Okay, so question 8 is talking about probability. And so this is like our chapter 5 stuff. And the first part, A, big A, capital A, says, suppose a bag of marbles contains 20 red, 10 white, and 5 blue. Find the probability that a randomly selected marble is either white or blue. Okay, so some keywords we're looking for here is, this is white or blue, right? So we notice that. And the question is, all right, so we reach into this bag, right? And you're just selecting one marble out, just one, right? So what's the probability that that one you pull out is either white or blue, right? Well, the probability of, first of all, let's figure out how many total marbles is this? 20 plus 10 plus 5, that's 35 total marbles. So I'm just going to write that here, 35 total. And so it says find the probability that you get white or blue. Well, to get white, I'm going to put probability of white is equal to 10 out of 35. The probability of getting blue is 5 out of 35. And so the probability of getting, I'm going to abbreviate W or B, white or blue, is equal to 10 over 35 plus 5 over 35, which equals 15 out of 35. And of course we want to reduce that. So let's see, 15 out of 35 is okay. So I have it as a decimal actually. So I'm going to calculate it real quick as a reduced fraction. I mean, gosh, I could do this in my head. I don't know why I'm having to use my calculator right now. 3/7. All right. So 3/7, or as a decimal, would be 0.4286. Yeah. And I actually approximated that. I rounded that to 4 decimal places. So the exact answer would be 3/7. Or if you round to 4 decimal places, it would be 0.4286. Yeah, I put it as at 4 decimal places on the answer key. So, okay. Part B says find the probability that 2 randomly selected. Okay, so in the first part, now I want to point out that on your formula sheet, when you notice that it says probability of E or F, right, that you'll notice that it says you have to subtract off the intersection, okay? And that's for dependent events. Now, if I'm just doing one event here, well, I guess not really one event. I guess let me start over again. On part A here, the question is, since I'm only drawing one marble out, is it possible that that one marble is both white and blue? And the answer is no. It's either white or it's blue. Or it's red, okay, but it's not going to be white and blue. So for that reason, when you subtract, quote unquote, subtract off the intersection, it's just 0. Okay, so I ignored that fact on this one. But on part B, when it says that, well, this one actually may be a little bit different, but find the probability that 2 randomly selected marbles are both red. Okay, now this does not say, I guess I should have been a little more specific here when I wrote this, that maybe I should say that this is without replacement. So, and I think you're just drawing, if you consider drawing them both at the same time, right? I'm just going to put a little note here. This is without replacement. Well, I can't really finish that set of parentheses there. Yeah, there it is. Okay. Without replacement. Okay, so find the probability that first red and second. So actually, hold on. I don't like the way I'm writing that. I'm just going to say red and red. Okay. So the probability of getting a red one, okay, and the probability of getting another red one, well, I need to figure out, okay, the probability that the first one, so I like to do my little boxes here. I'm going to say this is the first is red, This is the second red. Okay, so what's the probability that the first one I draw out of there is red? Well, there's 20 out of 35 total. So 20 out of 35. Okay, so I take a red out of the bag. Now, what's the probability that the second one I draw is a red? Well, I've taken one of the reds out already, so I'm down to 19 reds in the bag. And I took a marble out of the total, right? So I'm now down to 34 total. Okay, so for and type situations, this is when we multiply. For or situations, we add. Now, you're probably saying, well, it didn't say and, right? Well, you have to kind of figure that out when it says, find the probability that two randomly selected marbles are both red. Okay, so if both of them are red, that means the first one is red and the second one is red. So you kind of have to make that distinction there. Okay, so when we multiply those, and I did go ahead and just round this to 4 decimal places, it is 0.3193. There. Okay. So capital B says if 10%, did I really do that again? Oh my gosh. Okay, sorry. If 10% of high school students fail their standardized tests on the first attempt, find the probability that in a sample of 9 students, all failed on their first attempt. Okay, all failed. Okay, well, let's see here. What's the probability of failing? It says 10% of students fail, right? So 10% of students fail. So the probability of failing, 0.10 or 0.1, right? So that's for each person. That's their probability of failing, okay? So if I want to know the probability that a sample of 9 students all failed on their first attempt, okay? So that means that I'm going to take the probability that student 1 failed, the probability that student 2 failed, student 3, student 4, student 5, all the way up to student 9, that all of them failed, right? Now, these are independent events because the failure of one student does not determine the failure of another student. So these are independent. And therefore, when we see that whole, this is really your key, all of them. That's the biggest key word. The probability that all failed, okay? So when we say the probability that all of them failed, this is like all 9 fail. That means we're going to take the probability of the first one failing times the second one failing times the third one all the way out 9 times, right? Or in other words, we could say 0.10 to the 9th power. Okay? Now, if we want to write this in scientific notation, which is what the calculator is going to give us, that's going to be 1 times 10 to the negative 9th. Now, if I'm going to write it in standard form, that means I move the decimal to the left 9 times. So I'm going to have a decimal with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and a 1. Wow. Talk about low chances. So very, very small probability that will happen. That all 9 of these students will fail their standardized test on the first attempt. So now we go to part C, which says if 10% of high school students fail their standardized test on the first attempt, find the probability that in a sample of 9 students all passed on their first attempt. Okay, so all passed, right? So we need to know the probability that someone passes. Well, we know the probability that if they fail is 0.10. So then what would be the probability of passing, right? What's the difference between 1 and 0.10? Or you could say 10% and 100%, right? So if 10% fail, then that means that 90% pass. Or in other words, we could say 0.90. Okay, so if we want to know the probability that all 9 pass, okay, well, we take the probability of passing, which is 0.90, and we're going to raise it to the 9th power, right? So now when I multiply that, I get 0.3874. Not as high as I had thought it was going to be, right? But again, we notice when it says if you see something that says probability that all, Okay, this is your setup. Okay, the probability that all, whatever, this would be your setup. Okay, so number 9 is talking about combinatorics. So how many different random samples, this is like our counting methods and stuff. How many different random samples of size 25 can be selected from a population of 100? What is the probability of one particular random sample being selected? Okay, so how many different random samples of size 25 can be selected from a population of 100? Okay, well, does it give any indication that order is important here when we select these 25 random samples, right? When we make these random samples of size 25, does it say anything about the order matter or that the order matters? No, it doesn't. So we'll say, well, order does not matter. So if order does not matter, that means that we're going to use a combination. Okay, now if order does matter, we would use a permutation. So if order does not matter, we're going to use a combination. And so that's that NCR. And we need to know what N and what R is. So N, remember, is going to be your sample size, like always, right? So you have a total of, or I guess in this case it says from a population of 100. It's actually your population size, but in any case, this is your total, right? N is going to be the total things that you have to choose from. So N equals 100, total number of things I have. And then what is the size groupings that I'm making out of these 100? And the size of the groupings is going to be 25. So I should probably do some little color coding here. Size 25, that's my R. And then 100, let's just say population of 100. There we go. Okay, so for this one, this means we're going to be doing 100 C25. Okay, so how many different random samples of 25 can be made from a population of 100? In your calculator, okay, I'll show you how to do that. The first thing you want to do, because probably most of you don't have a calculator that's as updated as mine. So you're probably, if you have like an 83 or an older 84, go ahead and type in your 100 first. So 100, then we're going to go to math, and then yours will probably say PRB or PROB, but that's the one you're looking for. PRB for probability, or PROB, also probability. And you'll see that number 3 here is NCR. So if you go down to number 3 and just hit enter, it'll go ahead and put the 100 there. Now, if yours is an older calculator, it just has 100 in front, and then it'll say the C, and then right after it'll be blinking for you to put in the R, and we're going to put in 25. So again, mine puts it down here. Looks all pretty like on the paper and stuff, but that's okay if yours doesn't. Then hit enter, and we get this number. Notice the E23 at the very end of that. This is huge. It's a huge number. Your answer is not 2.43. It is 2.43 times 10 to the 23rd power. So when I come back here, and we will not write that in a standard form. Whoops. This is 2.43 times 10 to the, what did I say, 23rd power. Okay, yes, again, we're not writing that in standard form. The question then says, what is the probability? I guess I should make a note here that it's important to know how to set this one up, like this part here. Okay, so what is the probability of selecting one particular one, right? So it's almost like your lottery ticket combinations, right? So what's the probability that I select exactly one? Well, it would be 1 divided by 2.43 times 10 to the 23rd power. Okay, and if you're going to divide that like in your calculator, just to leave it still in scientific notation, we wouldn't want to leave it like this. Make sure that you put your denominator here in parentheses like that, so that when you divide, you should get this answer. 4.12 times 10 to the negative 24th. Okay, that would be the probability of selecting one particular sample. Okay, in how many ways can horses in a 10-horse race finish first, second, and third? So the question is the order important here? So does the order matter? I mean, if you come in first place, does that matter if you come in first or if you come in second? Or is there a difference? Of course there's a difference, right? Gold medal versus silver medal. This here, the order is important. So order matters. So for that one, this means that we're going to do a permutation. And I did show you guys there's actually two ways you could do this, so I'll show you both. You can do permutations, or you can use your slot diagram, kind of the blanks that I did. So order matters, which means we're going to do NPR. And still the same. N is your total number of items you're choosing from, and R is the number of groups you're making, right? So we're looking at first, second, and third place. So how many ways can horses in a 10-horse race finish? Okay, so in a 10-horse race. So that means that my N is going to be 10. And then it says finish first, second, and third. So first, second, third, that means there's 3 places that we're choosing, right? So, sorry, let me get to my color coding here. First, second, third, that means R equals 3. Okay, so I would do 10P3. Now we would go about doing this the same way we did the last one. You go to math, probability, but instead choose the one that has the P. Oh yes, make sure you type the 10 first on the screen, then go to the math probability menu. When we calculate this one, this is going to be 720 ways that these 10 horses, horses in a 10-horse race could finish first, second, and third. So that's all the different possible winning combinations that there are. So this is what they use actually, when they do at the horse races and stuff, when they're talking about the odds and things like that, probabilities and whatnot, they use a lot of this kind of stuff, right? So first you got to figure out what are all the total possibilities, right? And so when they say they have a 1 in whatever odds kind of thing, this is what they're using. Knowing all the different ways that it could happen. The other way I told you guys you could do this is you could just set up your blanks and say, okay, so this is first, second, and third place. So how many options do you have for first place? Well, there's 10. Once a horse finishes first, then they can't be second. So now you only have 9 horses left that could be in second. And then after that, you only have 8 horses left that could be in third. And if you multiply those 3 numbers together, oh, imagine that, you get 720. So that's the alternative way to do permutations. You can't do that with combinations. You can do that with permutations, though. All right. Continuing on with the probability stuff. This is now where we're going to be using a table. So a company is testing a new medicine for migraine headaches. In the study, 150 women were given the new medicine, and an additional 100 women were given a placebo. The results are in the table below. We need to fill in those totals so we can actually do stuff. So what did it say? Let's see here. Well, let's add these up. 132 plus 56 is 188. 18 plus 44 is 62. 132 plus 18, so this is the people that were given the medicine, and it said 150 were given the new medicine, so when we add those we get 150. It says that 100 were given the placebo, and so I'm going to fix that 150 there. So then total we have 250, and if you add the total column here or the total row here, they should both add up to the same thing, which is 250. That's your total. Okay, if one woman who participated in the study is randomly selected, find the probability that... Okay, now I want to make a little statement here. But before I do that, I'm going to pause and turn off my air conditioner because it's so loud. Sorry about that. I hope that wasn't really bothering you for as long as it was on. Okay, what did I want to say? I'm going to make a statement here. When you're asked to find a probability, right? It says the probability, find the probability, find the probability. Your answer should be something that's between 0 and 1 inclusive. Could be 0, could be 1. Generally, it's not. It could be, though, if it's impossible or certain. But otherwise, it should be between 0 and 1 always. So if you're looking at answer choices on a multiple choice test, and the question says find the probability, and you see an answer that says 1.3, that should tell you something. That's not your answer. It's not a probability, right? It has to be between 0 and 1. It has to be. That's like a given. It has to be. So that can help you kind of eliminate answer choices. Anyways, so probability that she was either given the medication or her headache lingered. All right. So when we see or, remember that I mentioned earlier, when you see or, that means you're adding. But you have to subtract off the intersection. I talked about the marbles, and I said, if you're drawing one marble out, can that marble be both blue and white at the same time? And the answer was no. It's either blue or it's white or red. But it cannot be both blue and white. So we didn't subtract off the intersection because the intersection was just 0. Okay, but we're looking at this here. The question is, can a woman be both given the medication and have a headache that lingered? And the answer is yes. There's like 18 of them up here, right? That said that they were given the medicine and their headache lingered. So we do have an intersection here. So we have to consider that when we're adding our probabilities. We can't just add the first two and then ignore the fact that those 18 women got counted twice. Okay, so when we say probability, I'm going to just say meds or how should I put that? Lingered, maybe? I'll say lingered for headache lingered. Okay, so we have to find the probability that she got meds plus the probability that the headache lingered minus the probability that she got meds and it lingered. Okay, so what's the probability that she got the medicine? Well, given medicine, 150 out of 250. Plus the probability that she had a headache that lingered. That would be 62 out of 250. Now, because I took this column here, the headache lingered, 62, and I took this row, the medicine one, you'll notice that when we added those up to get the 150 and the 62, that 18, like I said, was counted in both. It was counted here in this row. I don't know if you can see that. It was counted in this row here of the medicine. It was also counted in the column of the headaches that lingered. So we counted 18 twice, which means we counted more women than there actually were. So that's why we have to subtract off the 18 out of 250. Okay. And when we do that, we get 194 out of 250, which as a decimal equals 0.776. Okay, so make sure you know how to read these tables. Okay, find the probability on the next one here. Find the probability that her headache went away given that she was given the placebo. Okay, I know there's two givens there. I know that can be a little confusing. I believe on your test, it's not going to have the word given twice like this. So when you see the word given, okay, again, that is telling you what formula you need. So you're saying, what's the probability that someone's headache went away given that that person had a placebo? Okay, so we're only looking at the people that had placebos. That's the 100 people. There's only 100 people that had a placebo, right? I want to know out of those 100, which ones had a headache that went away. And that was 56 out of 100, right? 0.56. I'm going to go ahead and kind of demonstrate this with the actual formula. But I mean, to me, if you look at it that way, it's almost easier than doing it with the formula, but I'm going to go ahead and write this down. So probability that it went away given that they had the placebo. Okay, and the formula for that, now there's two ways you can do this formula. When you have a contingency table like this, you really kind of want to look at just the numbers. Like I mentioned, we're talking about 56 people out of 100 people. And just looking at the numbers in the table. Now, if you're given actual probabilities, then you would already, then you'd want to go ahead and use the one that's on the formula sheet that says P of, the only difference for what I'm telling you is that it's an N instead of a P. So I'm going to go ahead and write the N here. Just know that this means number of items in this category instead of the probability of. And I can show you both, but this is probably the easiest way. So the number of people that had headaches went away, and they took the placebo, divided by the number that took the placebo. Okay, so given that they took a placebo, what's the probability that their headache went away? All right, so the number of people who their headache went away and they had the placebo, we come up here and it looks like headache went away and they had placebo, that's 56. And then the number of people that had a placebo, that was 100. So 56 out of 100 is 0.56. All right. On your formula sheet, I know it doesn't have the ends. That's okay. You can still do it this way. The formula sheet has P's, which just means you take the probability. So in other words, if I'm looking at the probability, each of those numbers, this would have been 56 out of 250. This would have been 100 out of 250. And what ends up happening is those 250s cancel out anyways. So it's like one extra step to do it that way. You can if you want. I mean, you don't have to. Like I said, I think this is a lot easier. Okay, so number 11 says... we're doing simple probability, finding mean and standard deviation of a probability distribution. A social worker asked all of her clients, what do you believe is the ideal number of children to have in a family? The results of our survey are in the table below. A, find the probability that a randomly selected client believes the ideal number of children is fewer than 3. Fewer than 3. All right, so fewer than 3, what does that mean in a discrete situation, right? Like this is discrete, right? 0, 1 through 4. This is a discrete probability distribution here. And so fewer than 3 would be 0, 1, or 2. All right, so I want to know what's the probability that they believe it is fewer than 3. Well, if I just take each of those probabilities, so probability of 0 plus the probability of 1 plus the probability of 2, and I add those up, that would be the probability of being fewer than 3. Okay, so probability of 0, 0.011. Probability of 1, 0.033. Probability of 2, 0.578. So if you add them all up, you get 0.622. Easy as that. All right. Find the probability that a randomly selected client believes the ideal number of children is more than 1. Okay, so again, in this discrete situation, what does more than 1 mean? And you're going, it means more than 1. I'm like, I know. But what numbers would those be? More than 1 would be 2, 3, and 4, right? 2, 3, and 4 in this problem. So we're going to take the probability of 2 plus the probability of 3 plus the probability of 4 and calculate that. Well, probability of 2 we said was 0.578. Probability of 3 is 0.278. Probability of 4 is 0.100. So if I add all of those numbers up, I'm going to get 0.956. Well, it looks like a lot of people believe that you should have more than one child, according to this. So, I guess. There you go. There's a couple more questions about this table on the next page, I believe. Yes, there are. So we may have to come back and reference this page. Let's see here. It says, find the probability that a randomly selected client believes the ideal number of children is at least 2. Okay, what does at least 2 mean? This is the one that everybody messes up. Like, at least 2, people are like, oh, it means less than 2. No, it doesn't. At least 2. At the very least 2. That means 2 or more. Right? So I'm going to put here 2 or more. Okay. I believe we already just found that, right? 2 or more, we said, is 2, 3, and 4, right? Well, we already found that. So I'm going to go ahead and just write it again. Probability of 2 plus the probability of 3 plus the probability of 4, which is 0.578 plus 0.278 plus 0.100 0.956. Okay, this is just another way to say it, right? At least 2 is the same as more than 1. Okay. Find the probability that a randomly selected client believes the ideal number of children is at most 1. At most 1. Okay, what does that mean? At most 1. At the very most 1. That means no more than 1. So 1 or less, right? So 1 or less. Well, in this case, that would be 0 and 1, right? So probability of 0 plus the probability of 1, is what we're looking for. So probability of 0, let's go back. Probability of 0 is 0.011 plus 0.033. Okay, so if I add those two together, I get 0.044. That's a fairly small probability. So let me ask you this question. Would that be unusual for someone to say that they believe the ideal number of children is at most 1? Yes, that would be unusual. That's less than 0.05, right? So yeah, that's unusual. Okay, part E says to calculate the mean of the distribution, report with correct symbol, and rounding. All right, so the mean of the distribution is also called the expected value. Okay, so the expected value, or mean, is, I think you're going to find pretty easy to do, that you're taking so you've got your x's here and their probabilities. In order to find the mean of this distribution, you are finding the sum of the x times p of x. So, in other words, the expected value, let me write this down here. Expected value, or e of x, is equal to the sum of x times p of x. Okay, so if we take x times p of x, so that p of x is like the frequency, right? So if you set it up in your calculator, you've got your 2 columns. Your first column, that's going to be your x's. So let me show you that. Okay, so we're going to go to Stat, Edit, and in my first column here, I'm going to go ahead and put my 0, 1, 2, 3, 4. And then in my second column here, I'm going to put their probability. So 0.011, 0.033, 0.578, 0.278, and 0.1. Okay, so the order here, of course, is important because each of these x's, that is their probability. So if you change order, then that messes everything up. So don't change order. Make sure you keep them in the same order. And you're going to go to Stat, Calc. You're going to use your 1var stats from way back when. List 1, that's going to be your x's. That's L1, right? The list. And then for the frequency list, we're going to go ahead and use L2, the probabilities. Those are our frequencies now. Second L2, and then we are going to calculate. And there at the top, you'll see your mean, right? 2.423. Remember that we're always going to round our mean and our standard deviation to one more decimal place than what our data was. Our data in this case was all those x values, 0, 1, 2, 3, 4. So those are whole numbers, right? So I'm going to round to one decimal place. So 2.4. Okay. And for the expected value, you could say E of x, or you could say mu, and that's going to be equal to 2.4. Now, you're probably wondering why I didn't put x bar, because that's what it showed on the calculator, right? Why do we not put x bar? Well, we know that this is the whole population. I mean, this is a probability distribution, so expected value is the population mean, and therefore we use mu. Now, this is also on your formula sheet, so if you look on your formula sheet, which I thought I had in front of me, but I'm now seeing that I don't have it in front of me. Where did I put it? Anyways, there it is. It's on the formula sheet. I know it is. I just have to find it. Okay, here we go. Yes, expected value is on chapter 6. And so that's exactly how it's written here. So that's what it is. 2.4. That's it, 2.4. So I'm going to go ahead and just box that up. Okay. And then part F says calculate the standard deviation of the distribution, report with correct symbols and rounding. So again, the standard deviation, this is going to be sigma because this is a population. So when you look on your calculator, you are looking at sigma. So luckily we can see it right here. It's 27.04. So that 0 is just going to stay a 0, right? Oh, am I looking at the wrong thing? Wait a minute, hold on. Wait, that's not the right thing. Oh, that was weird. Okay, so that was like, I was like, that number does not seem right. Okay, well, caution, apparently. That was leftover stuff from something else. Yeah, if you look now, you'll notice that the S here, there is nothing for sample standard deviation. There is for the sigma, though, for the population standard deviation like there should be. And it is 0.75. Okay, this is much better. This is a much more believable number here. Okay, so 0.75, if you round that to one decimal place, it would be 0.8. Man, I can't believe it. I don't know what it's showing there. That's so weird. Okay, 0.8. I thought we were all lucky, and then we almost got the wrong answer. Okay, so 0.8. That's it. Okay, number 12 says, a company makes electronic gadgets. 1 out of every 50 gadgets is faulty, but the company doesn't know which ones are faulty until a buyer complains. Suppose the company makes a $3 profit on the sale of any working gadget, but suffers a loss of $80 for every faulty gadget because they have to repair the unit. Find the expected profit for the company, then estimate their total profit if they sell 150,000 gadgets. Okay, so you'll notice a keyword here, and it is expected. So expected profit. All right, when you see the word expected, again, this is telling you you're going to do expected value, which is just the mean. But we are doing it with a probability distribution. So we need to figure out our x's and our probabilities of x's. So what are our x's, right? So we've got a couple things that we're talking about here. We're talking about things that work and things that don't work, right? We're talking about gadgets. You've got 50 gadgets. 1 out of every 50 is faulty. It means it doesn't work, right? And then that means the other 49 have to work, right? I mean, that just makes sense. So I'm going to go ahead and write here, I'm going to go ahead and put x. Actually, I'm going to put the x here. Put probability of x there. And over here, I'm just going to go ahead and say faulty works. Okay. X is going to be our profit, right? This is how much, or profit or loss, I guess I should say. This is the amount of money that we make or lose, depending on the fact that our thing is either faulty or it works, right? So if our electronic gadget here is faulty, how much did it say we make or lose, right? It says it makes $3 of profit on the sale of any working gadget. Okay, so here I'll do this. Makes $3 of profit for working ones. Okay, so that means this one here is going to be a big positive 3. Make $3. Okay, and then it says it suffers a loss of $80 for all the faulty gadgets. That means that's a big negative 80. Okay, and then the probabilities, right? Now that's the tricky part. How do we figure out the probabilities? Well, what did I say just a little while ago? It says 1 out of every 50 is faulty, right? So the probability of being faulty is 1 out of 50. I mean, you could also write that as 0.02 if you wanted to do decimals. Now, if we said one of them is faulty, then we said the other 49 must work, right? So 49 out of 50 or 0.98. Remember, your probabilities have to total up to 1, right? This is the whole set, right? It's either faulty or it works, and that's it. So when we're looking for the expected value, you could put this in your calculator like we did that last problem, but I mean, there's only 2 numbers here. Well, 4, I guess, technically. There's only a couple of things that you have to multiply. So I'm going to go ahead and use our formula here and multiply x times p of x. So negative 80 times 0.02 is negative 1.6. And 3 times 0.98 is 2.94. Okay, so if I add those up, right? So here this is going to be the sum of the x times p of x. In other words, this is the expected value, expected profit, right? By the way, I knew that x was my profit. I should say that here. X is the profit. Because it tells me find the expected profit, right? So that's how I knew x was going to be my dollar amounts and stuff. Okay, so if I add those up, I should get 1.34. Okay, so what does this mean, right? This is a positive number, yeah? So if your expected value is positive, and you're talking about x being a profit, this is a good thing. You want that to be positive. You want to be making positive profit. You don't want that to be negative. If that's negative, that's a problem for your company. That means you're losing money, right? And you're not making money at all. So you want that to be a positive number. So what this means, this is a $1.34 in expected profit. If I was going to kind of explain in words what that means, I would say that the company in the long run expects to make $1.34 on every gadget in the long run, right? The question, though, it doesn't ask me to interpret that, but that's how you interpret it. Find the expected profit, then estimate their total profit. Okay, so now estimate total profit if they sell 150,000 gadgets. Okay, so if they're selling 150,000 gadgets and we're expecting to make a profit of $1.34 on every gadget in the long run, right? So 150,000, that's a long run. What would be an estimate of our total profit? Well, if we expect to make $1.34 on each of these 150,000 gadgets, 150,000 times 1.34, what does that equal? That equals $201,000. So this means that I'm expecting, or an estimate for my total profit. If I sell 150,000 gadgets, this would be an estimate for the total profit, right? So I would say, how do I want to word that? Total profit for selling 150,000 gadgets is $201,000. This is my expected value. I'm going to box that too. Okay. Number 13. This is a question about binomial experiments. So we have to go through kind of our 4 requirements to see if something is binomial. So the 4 requirements for that. First one, so I'll read the 4 requirements from my formula sheet. 1, there are a fixed number of trials in the experiment. That's the first thing. 2, the trials are independent or n is less than 0.05 capital N. So that means that your sample size is less than 5% of your population size. Number 3, the probability of success on a single trial remains constant throughout. And then number 4, there are only 2 outcomes possible in each trial. So that would be binomial. Okay, so which of the following is a binomial experiment? Okay, A says randomly interview 35 Americans asking if they voted in the prior election. Okay, well, let's start with, is there a fixed number of trials? So, number 1, fixed number of trials? Question mark. The answer is yes, there is. N is 35, right? That is, oops, that's not what I wanted. 35 Americans. That's my N. Okay, so N is 35. So it says fixed number of trials. That means you have a fixed number of, people, or your sample size is fixed, right? Okay, second thing that we want to verify is trials are independent. So trials independent. Or in other words, is N less than, or sorry, I'm going to actually go ahead and rewrite this the way we've been doing it in our class, which is N divided by 0.05, is that less than or equal to the entire population? Okay, well, if we're talking about 35 Americans versus all Americans, I think we're safe to say that that is true. I mean, I can go ahead and verify it. I'll show you. Oh, I didn't say yes here. I should say yes. 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 I'll verify. Okay, so 35 divided by 0.05 is equal to 700. Yeah, I think that's well below all Americans. So that's a yes. Okay. Number 3, the probability of success on a single trial remains constant. So probability constant. Okay, well, it says asked if they voted in the prior election. So they randomly interviewed. I would say the probability is constant here because, we don't know what the probability is, but yeah, it looks like it's going to be, constant, right? I would say, was it 50-50? Maybe, because they either voted or they didn't. Yeah, I don't know what the probability, but I would say that it is constant. So, the fourth one is only 2 outcomes possible. So, only 2 outcomes possible. And the answer to that one is yes, they either vote or they didn't. So vote or didn't. So that's a yes. So yeah, I think I'm questioning probably. I have a hard time with these. These are hard for me. Let's see. Randomly interview 35 Americans asking if they voted in the prior election. I would say the probability is constant. I would say that it could be 50. I would not say it's 50-50, but I would say that it's constant. It doesn't seem like that's something that's changing from person to person, right? So it says the probability of success on a single trial remains constant. So what that means is that is the probability that the person voted or didn't vote going to be the same for each person? And I would say yes. I don't have a hard fact here, like I don't have a P. So I would go with this is binomial, right? So this is binomial. Although if I probably should rewrite this question and actually throw a probability in there for you. Making sure that that's a little more clear. Okay, B. Randomly selecting 10 days out of the summer. Summer has approximately 92 days. And recording if each day at a veterinary clinic had at least 15 patient visits. Well, let's see. If we can just find one thing that doesn't work or doesn't have, it doesn't arrive at a yes, then we would say that it's not binomial. So all we really have to find is a counterexample for any of those 4 items. So, when I see what I'm looking at here is, I think that there's a couple, I don't know, let me see. There are a fixed number of trials in the experiment. Randomly selecting 10 days out of the summer. Summer has approximately 92 days. All right. Okay, so if you take 10 days, seems like a fixed number of trials. Trials are independent. So let's see here. If I did 10 divided by 0.05, what does that equal? 10 divided by 0.05, that's 200. It says that there's approximately 92 days in the summer, right? So the population is only 92. So this is not less than or equal to 92. So these are not independent. Because of that fact. So that's what we're noticing there. And so because it's not independent, I would say not binomial. Okay. C, randomly survey 50 traffic lights. I don't know how you survey a traffic light. But you randomly survey 50 traffic lights in a large city at 3 p.m. and record if the light was red, green, or yellow at that time. Okay, well, if you're recording whether it's red, green, or yellow, how many outcomes is that? Sounds like more than 2. So there are more than 2 outcomes. So outcomes would be green, red, and yellow. So there's not just 2. So not, well, how do I want to say that? I'll say this, more than 2 outcomes. More than 2 outcomes. Not binomial. Okay, D. Guessing randomly at all answers on a quiz that has 10 multiple choice questions with 4 answer choices on each question and 5 true-false questions. Okay, well, let's see here. What are we looking at? So is there a fixed number of trials? Sure, there's 10 questions, right? So yeah, trials are independent. I would say yes. The probability of success on a single trial remains constant. That's where we run into a problem here because it says 4 answer choices on each question, and 5 true-false questions. So 10 sorry, there was 15 questions on this test. 10 of them are multiple choice, 5 are true-false, which means that their probability of guessing correctly is going to be different on the ones that have 4 answer choices versus the ones that are true-false questions, right? So the probability here is not going to be constant for each trial. So each question has a different probability. Like, well, these 10 multiple choice questions, they all have a 25% probability of success, right? But the true-false questions have a 50% probability of success. And therefore, the probability is not constant for each trial. So I'm going to say probability for multiple choice is 0.25. Probability for true false is 0.50. So we say probability is not constant. For each trial. So it's not binomial. Okay, and then the last one, toss a fair coin until you obtain 10 heads. Okay, well, if you're going to be tossing it until you get something, that means that you don't have a fixed number of trials, because you're going to keep throwing it until you get to 10 heads. So maybe the first time you do the experiment, it's 10. You got 10, you got heads on every time you flip the coin, right? But maybe the second time you did it, it's 20. So you get 20 coin flips until you got 10 heads. So each time you perform the experiment, it's going to be a different number of trials. So this one has no fixed number of trials. So this is not binomial. And really that keyword is the until part. Okay, let me see what I'm doing on time here. Okay, perfect. I think this is good. Next 4 pages are done on this video, so probably going to be doing 2 more videos, dividing up into fourths. So this will be the end of this one, and then I will start with question number 14 on our 3rd video.